In this question, three identical solid cylinders are kept as on a horizontal surface. Find the initial acceleration of topmost cylinder after the system is released from rest for the two cases. The first case is there is friction between two cylinders and ground, but there is no friction between the cylinders such that there is no slipping between ground and the two cylinders. So we have friction at this contacts only. The contacts between the cylinders are frictionless. And the second case is there is no friction with ground, but there is friction between the cylinders, friction between these contacts, like these contacts between the cylinders, such that there is no slipping between the cylinders. There is no slipping between the cylinders here. So let us first discuss the case number 1, when there is friction between the two cylinders and the ground. Let us just make the free body diagram in the first case. So there will be normal reaction between the cylinders, between cylinders A and B, between cylinder A and C. B will have a tendency to move towards the left and C will have tendency to move towards right. So there is no normal reaction between B and C. There is normal reaction between B and ground and normal reaction between C and ground. And in absence of friction, this B obviously will move towards left. So this has a tendency of moving towards left. So friction is towards right, and on this friction will be towards left. So let us make the free body diagram. So in free body diagram, there is normal reaction which will be along the common normal. So this is the direction of common normal here. So this is normal reaction on A and this is normal reaction on B. I am not making the free body diagram of C. C is equivalent to B. So there is normal reaction between A and B. Let us write this normal reaction as N. So this is N and this is also N, action reaction pair. And there is Mg acting on A, and there is a normal reaction between A and C also. And since I am drawing the free body diagram of A, let us draw the normal reaction on A only. So I am just drawing the normal reaction on A only, and by symmetry this normal reaction is also equal to N. There is one force, gravity, on this A. Gravity is, let's say this is equal to mg, all have equal masses. Now this B will accelerate towards left. So acceleration of B will be towards left. Its acceleration will be towards right. And obviously the acceleration of A will be in the downward direction, because these two normals have vertical components and their horizontal components will be cancelled. So net force on this A will be along vertical direction. So acceleration is obviously in the vertical direction. So let us write the acceleration. This acceleration is suppose A, and suppose this acceleration is A dash, and this acceleration is also, by symmetry, this is also equal to A dash. Now to find the acceleration of A, suppose we know mg and we have to calculate these normal reactions. If we calculate this normal reaction, then using the geometry and all, we can find the net vertical force on A, and by the net vertical force on A we can find the acceleration of A. So we have to find this normal reaction, and to find this normal reaction we have to consider free body diagram of B. Since B is moving towards left, it has tendency to move towards left, so friction on this will be towards right. So friction is acting like this. This is friction, and this is friction on this C. So friction will be like this, and due to this friction there is torque on B, and it will rotate like this. Suppose its angular acceleration is alpha, so it is rotating with angular acceleration alpha, and obviously it is also rotating with angular acceleration alpha. There is no rotation of A, since all the forces are passing through the center of mass. The two normals are passing through center of mass, and mg is also passing through the center of mass. And what will the geometry, we have to use the geometry involved in this question. So joining the three centers will give an equilateral triangle at this particular instant when they are just released. So I'm joining the three centers, and joining three centers will give me this equilateral triangle. So these normals are along this equilateral triangle. These are the sides. Normal are along these sides. So this is your normal reaction. One normal reaction on this B will be like this. This is the normal reaction, and this normal reaction is making an angle 60 degree with the horizontal. So this is horizontal and this angle is obviously 60 degree. So normal reaction in this diagram will be at an angle 60 degree with the horizontal. So this is the geometry involved. So anyhow, we have to find this acceleration, and for this acceleration we have to consider the free body diagram of this B, and from free body diagram of B we should write the equation in the horizontal direction, because in the vertical direction there will be one more normal reaction, and I want to avoid this normal reaction. Suppose this normal reaction from the ground is N1, and we have to try such that this normal reaction is not involved in our equations. So I'm writing equation on B in the horizontal direction. So Newton's laws of motion, second law on B along horizontal. So what are the forces along horizontal? One is component of normal reaction, this is component of normal reaction, and one is friction here. And acceleration is also towards left. So towards left is obviously the positive direction while I'm writing the equation for B. So normal reaction has component n cos 60. So this is n cos 60, which will be n by 2. So this is n by 2 minus this friction. This is equal to m a dash, mass is equal to m. So this is our equation number 1. Let us write the equation of torque on this B. So torque is equal to I alpha. I am writing torque about Cm is equal to I about Cm into alpha. And since this B is rolling without slipping, there is no slipping between B and ground, and this is alpha and this is a dash. This point at this particular instant there is no angular velocity, so this point has acceleration a dash in this direction and alpha into r in this direction, where r is the radius. And for no slipping, the condition will be alpha dash is a dash is equal to alpha into r. So torque about center of mass, which force will produce center of torque about center of mass? Normal is passing through center of mass, mg is passing through center of mass, and this normal direction n1 is also passing through center of mass. Only friction is producing torque, and this torque is obviously F into r. I about center of mass is mr square by 2, and alpha we can write a dash by r. So all the r in this equation will be cancelled, and this will be F is equal to m a dash by 2. From these two equations we can eliminate this frictional force, and by adding 1 and 2, let us add 1 and 2, 1 plus 2, this will give n by 2, this is equal to 3 by 2 m dash, and 2 and 2 are cancelled, and this will give n is equal to 3 m dash. So we can get this. We can also write the torque equation about instantaneous axis of rotation or instantaneous center of rotation. So this point, the bottommost point, since there is no slipping and ground is also at rest, so this point is the instantaneous center of rotation or instantaneous point which is at rest. So we can also write the torque equation, and also at this particular instant there is no acceleration of this particular point because there is no angular velocity and all. So this point has zero acceleration. This is inertial point also, so we can very well write the equation of torque about this point. So there can be alternative. Torque about instantaneous axis rotation is equal to I about instantaneous axis rotation into alpha. Now we have to see which force will produce the torque about this bottommost point. So let's draw this. So this is the bottommost point. Obviously n1, normal direction from ground, will not produce any torque. Friction will not produce any torque. Mg is also, its weight will also pass through this point. So only force which can produce torque about this point can be this normal reaction, because this normal reaction between the two cylinders A and B will go like this. So let us draw that. So this is the normal reaction which is passing through this center. This is the line of action of the normal reaction, and we can drop perpendicular from here. So dropping perpendicular, we have to find this perpendicular distance to find the torque due to this normal reaction. And what is this perpendicular distance? Just join these two. Normal is making an angle 60 degree with the horizontal, and from this vertical it will make angle 30 degree. So this angle is 30 degree. This is equal to radius, and obviously then this is equal to r sine 30, and r sine 30 is r by 2. So torque of normal reaction will be n multiplied by r by 2. So this is the only torque which is about this point. What is moment of inertia? Moment of inertia will be about this. This is a mr square by 2, and about this we have to add mr square according to parallel axis theorem. So this will be 3 by 2 mr square. This is very easy. 3 by 2 mr square, and alpha is equal to a dash by r. So from this also we can write n is equal to 3 m dash. The only benefit is we have to write just one equation, and in this method we have to write two equations, and friction will come into the picture. So we have find normal reaction, but normal reaction is coming in terms of a dash, and we have to find the acceleration a. So we must find normal reaction in terms of a, then only we can find the acceleration. And we have to relate a dash and a. There must be some relation between a dash and a, because these are rigid bodies. Rigid bodies in contact are moving, so there must be some relation between these two acceleration a and a dash. Let us do this in general. I am finding the constraint relation at any general instant. Suppose it is like this. It has suppose shifted somewhat like this. It has shifted somewhat like this, and let us join this. All these are moving in contact. It has velocity in the vertical direction. Let's say this is velocity v, and it has velocity in the horizontal direction. Let's say suppose it is v dash, and I'm assuming this angle is theta. This angle at the initial instant will be equal to 30 degree, but as these are moving, this angle will change because this distance will be changed. So at a general instant, suppose this angle is theta, and we are supposed to find the relation between their accelerations, and let us say v and v dash. We are finding the relation between v and v dash from rigid body constraint. From rigid body constraint, we know that there should be no relative motion. There should be no relative motion perpendicular to the contact surface, in a direction perpendicular to the contact surface. So this dotted line is denoting the normal direction. These two are in contact like this, and this will be the contact surface, and line joining the center will be the common normal direction. So there should be no relative motion along this normal direction perpendicular to the contact surface. There should be no relative motion. So there should be no relative motion. That means component of velocities along this direction should be equal. So component of this velocity v along the normal direction will be v cos theta, and this component, this angle is 90 minus theta, this angle is also 90 minus theta. So this will be v dash cos 90 minus theta. So this will become v dash sin theta. So this is v dash sin theta, and this is v cos theta. And these two components should be equal from the rigid body constraint. There should be no relative motion along the direction normal to the contact surface. So we can write v dash sin theta is equal to v cos theta. So this v dash is equal to v cot theta. This is the relation between velocity. So we must keep in mind that this kind of statements and this kind of relation hold only for velocities. not for acceleration. These relations only hold for velocities or displacements. For a very small displacement, for very small displacements or instantaneous velocities, these relations hold, but these relations does not hold in general for acceleration. I cannot write straightforward a dash is equal to a cot theta. That will be wrong. That may be correct, but that is in general wrong. So v dash is equal to v cot theta. If I differentiate this, then this is dv dash by dt. This will be dv by dt into cot theta, and since theta is also variable here, so v cot theta minus cosec theta cot theta, sorry this is cosec square theta and d theta by dt. The important term is d theta by dt, and this d theta by dt is not 0 in this particular case, but at the initial moment velocities are 0, and since velocity is 0, so this whole term will be 0. So we can write further, this is 0, so we can write a dash is equal to a cot theta. So the relation which holds between velocity is true for acceleration also in the case when velocities are 0. So when velocity is 0, then this relation is also applicable for acceleration. This is very important here. And in our case, at the initial moment, this angle is 30 degree and cot 30 degree is root 3. So we can find the relation between a dash and a. A dash is equal to a root 3. From here, we can write this normal relation is 3m. For a dash, I can write a root 3. So n is equal to 3 ma root 3. And from this, now we can easily find the acceleration of this topmost cylinder. For topmost cylinder's acceleration, we have to just write the net force in the vertical direction. And what is the net force in the vertical direction? Mg minus component of normal relation is n cos 30, and this will be twice 2n cos 30. This is equal to ma. And for normal relation, we can write this 3 ma root 3, and cos 30 degrees root 3 by 2, this 2 and this 2 will be cancelled. So this is mg minus root 3 into n, and n is equal to 3 root 3 ma. This m is cancelled here. Now this will be 9, and this 9 will go here, it will become 10. So acceleration is g by 10. So for the first case, the acceleration of the topmost cylinder will be g by 10. This is the answer for the first case. Now we are solving for this case number 2. In case number 2, we have frictions between the cylinders, but there is no friction between cylinders and ground. So cylinders are not slipping with respect to each other. So for A, again there will be normal reaction which will pass through the center and mg, and now there will be frictions also such that it is not slipping. What is the direction of friction on A? Since it has downward acceleration, so it is coming in the downward direction, and this contact point will also come in the downward direction, and it will have a tangential component rightwards. If this point has acceleration downward, so it has tangential component will be like this. So this point tends to slip in this direction, so friction will be in this direction upwards. Again, at this location also friction will be in the upward direction. So let us draw the free body diagram in this particular situation. So at contacts, obviously there will be normal direction, and friction is also there. So friction on A I am drawing. This friction will be like this, and here this friction will be like this, tangential. So these are the two frictions. So one normal on A will be like this, and other normal will be like this. These are the two normal reactions. Friction on B will be opposite to this action reaction. So this is friction on B, and this is friction on C. This is normal reaction on B. I am not drawing the normal direction between B and ground and mg of B. I am interested in horizontal direction only. For A, acceleration will be downward direction. This is A like before. So this is acceleration of A and this is acceleration of B. So this is acceleration of C. Acceleration, this is A and this is A dash and this is A dash. From the previous question, we can also write the relation between the accelerations, and relation between the accelerations will be same as in the previous question. So I'm just writing straightforward, A dash is equal to A root 3. So this is our first equation. This is the normal direction and this is normal direction and this is also normal direction, and by symmetry these two frictions will be equal and these are also equal to F. Now equations we have to write. First I am writing the equation on A. To find acceleration of A, we have to write the equation in the vertical direction. There is one more force which is mg here. So on A we have to write this mg. Component of normal reactions, this will be 2n and this is equal to 60 degree. So this is 2n sine 60 degree, vertical component sine 60, 2n sine 60, and for friction it is 2f cos 60. This is equal to ma. From this equation we can find the acceleration of this A. So this is our equation number 2, and to find the acceleration we have to find this friction force, we have to find this normal reaction. Now we have to write the equation on B. For B we can write the equation of for linear motion, Newton's laws of motion. So for Newton's laws of motion I am writing the equation along the horizontal direction, and along horizontal component of normal will be n cos 60. So this is n cos 60. Component of friction will be in the minus towards right, f, it is sine 60. This is f sine 60, and now this is equal to m dash. This is our equation number 3. Now rotation, we have to consider rotation. There is no rotation of A because normal is passing through the center, mg is passing through the center, and this friction will tend to rotate in the clockwise direction and this friction will tend to rotate in the anti-clockwise direction. So all the effects are cancelled. So A will not rotate. B, normal direction passing through center, this normal direction will pass through center, mg will pass through the center, but due to friction tangential force it will rotate in the clockwise direction. So this B has tendency to rotate in the clockwise direction. Let us assume its angular acceleration is alpha, and obviously this will rotate in the anti-clockwise direction with same angular acceleration alpha. Now obviously we cannot write straightforward A dash is equal to alpha into r, because that condition is true at this particular location, but at this particular location it is a frictionless surface, so there will be slipping at this particular location. So we cannot write that A dash is equal to alpha into r straightforward. We have to write the conditions for this. Condition of no slipping we can write here, right at this location. But before that I am writing the equation of torque is equal to I into alpha. So for B, torque about Cm is equal to I about Cm into alpha. Since there is no point of this instantaneous axis of rotation which is very clear in this particular situation, so straightforward we are using this option, torque about center of mass is equal to I about center of mass into alpha. Which force will produce torque? So only friction is going to produce the torque. So this is F into R, and I same is simply mr square by 2, and I am writing it as alpha. So 1r is cancelled. So from here F is equal to mr alpha by 2. This is the fourth equation. Now we have to write one more equation for no slipping condition. There is no slipping between the cylinders, so for no slipping condition, for no slipping condition, what we can write, we have to use this point for no slipping condition. Already we have used this contact for our constraint relation. We have written constraint relation. Now we are using no slipping condition. No slipping means there is no relative motion along the contact surface. For that At the initial moment, we have to equate the accelerations for no relative motion. So for B, what is the acceleration of this contact point, and for A, what is the acceleration of this contact point? So for A, the acceleration is vertically downward, and what is its component along this contact surface, along the tangential direction? So what is this along the contact surface? So this A will be what is the angle? First we have to find the angle. So this angle is 60, this is 30, and this angle is again 60 degrees. So this is A cos 60. So this component is A cos 60. For B, what is the component? This point has contribution from the translational acceleration and alpha. Due to alpha, it has already tangential acceleration alpha into r in this direction, and due to this A, you have to take the component of this A dash. What is the component of this A dash along this tangential direction? This is the direction of A dash, and we have to take its component along this direction. So this component will be, this angle will be 30 degree. So this is A dash cos 30 degree. So along the contact surface, acceleration should be equal. So this point has acceleration slightly in the downward direction, A cos 60, and this point has downward acceleration alpha r minus A dash cos 30 degree. So our no slipping condition will be A cos 60 degree, this is equal to alpha r minus A dash cos 30 degree. And wherever A dash is coming, we can replace this A dash by A root 3 from the equation number 1. So this is the fifth equation, and we require 5 equation because we have variables. If we count the variables, one is A, one is A dash, one is this alpha, one is this normal direction, and this fraction. We have 5 variables. So after solving these 5 equations are not very difficult to solve, so we can easily solve these equations. So after solving these equations, we can find the required acceleration A as g divided by 11. So this is the answer for this question.